Welcome and good afternoon, good evening, whichever time you're watching this. Welcome to Let's Talk Chemistry with Pastor Dan. So we're looking today at the structure that makes up electrons and how we find their arrangements. Before we do that, let's go back and real quick review about the atom. So here's atomic structure. So if we look at this, this is a model of the atom. So we have this big old ball here, and that would be of these five. Hopefully you know that that is my nucleus. And then what two particles go inside the nucleus? That would be the neutron and the proton. All right, this little bugger that sits out here, that's my electron. And do electrons go in clouds or orbits? Well, hopefully remember they go into clouds. Now, when we arrange electrons, we're able to identify where they're at by the spectrum of light emitted, something we call emissions. So either line spectrum or dark line spectrums. We identify by, we're going to talk about how the process takes place. Now, in order to do that, we first need to talk about what the spectrum is, and that's a full range of light that exists. We go all the way from radio waves, TV waves, cellular waves, and there's a lot of other ones inside. Infrared, just the other side of the visible spectrum. I always tell students that can we see in the infrared? Well, if we can see in the infrared, then we slither on the ground and we spit out our tongue all the time. We're a snake. Visible spectrum, red, orange, green, yellow, blue, indigo, violet. And the other side of violet is ultraviolet. Again, we can't see in that one either unless we're certain breeds of insects. And then we have the micro, the gamma, the cosmic. And as we're going out, the frequency is getting higher. The wavelength is getting shorter. So a long one and a small frequency. That's how the spectrum works. Now, how does this process actually take place? I found a video that I'm going to include here. Pop in real quick. Probably gonna get a commercial. Yes, we
things
are.
perfectly organized, I'll start working on my thesis.
There we go. Skip it. There we go. So we have an electron at a base energy state. There's two excited states and there's a ground state. So when an electron is hit with energy of a certain type, in this case it's energy in the form of frequency and what we call Planck's constant, it excites the electron. The electron spikes up. Now if we're doing a black line spectrum, that line will be missing there, and that's how we identify where the electron was. Now it can't stay there because of the fact that that's not its natural state. So after so long sitting in that state, it loses its energy. It drops back down to its ground state, and it releases energy that we're able to see, and that energy then is able to tell us where those electrons are located. Now, we do that process through something called emissions equations. There's two equations that we talk about. We have, that's a fancy letter, that's a Greek letter that's called nu. Nu is equal to C over lambda. I always tell my kids, hey, what's nu? C over lambda. You don't get that? U will before the over. So then we go to the second equation, E equals H times nu. So what do these values mean? Nu means frequency. Frequency is expressed in hertz, which means per second when we work with it. But whenever we're trying to report it, it's expressed in hertz. A frequency is the number of waves, number of time a wave passes a point in a given time. Now, lambda is wavelength. Wavelength is expressed in nanometers. And a nanometer, 1 meter is equal to 1 times 10 to the ninth, a billion nanometers. And the definition of wavelength is it's the length of the wave. E is energy, expressed in joules. H, with that little hat on top, we call that Planck's constant. Not Planck, Planck, he's a Frenchman. The value there is 6.63 times 10 to the minus 34th joules second. We'll need that to find energy. And of course, C, we're going to express this 3 times 10 to the 8th meter per second. It's actually 2.98 something. Just make it easier. And that value helps us understand. So what's new? C over lambda. All right, so let's try a problem here. Determine the frequency of a light emission if its length is 357.90 nanometers. So let's do a graphic organizer. We'll start with our equation. What's new? C over lambda. And our values, frequency, we don't know because that's what nu is, frequency. C is 3 times 10 to the 8th meters per second. Lambda, our wavelength, in the problem it says the wavelength is 357.90 nanometers. So let's put our values in. We've got to convert that to meters because this one is in meters and this is in nanometers, so we got to get in the same unit. So remember we said that 1 meter is 1 times 10 to the 9th nanometers. We do the unit conversion with nanometers on the bottom, meters on the top, so that my nanometers will cross out. And I get 3.57 times 10 to the minus 7th meters. I then take my C value, 3 times 10 to the 8th, divided by 3.5790 times 10 to the minus 7th meters. Now when we divide them, we've got to remember our sig figs. This is a constant, so it's definitely significant. And I have 1, 2, 3, 4, 5 sig figs there. So my answer is 8.3822 times 10 to the 14th. Now that's per second, but remember we're expressing it. I'm asking for frequency. So how do we express frequency? Ow! Remember that's hertz. All right, awesome. And that's our answer. Let's try another one. Calculate the wavelength of emission when the frequency of the wavelength is 2.944 times 10 to the 14th hertz. So again, our equation here, what's new? C over lambda. New this time, we have the value, which is 2.944 times 10 to the 14th hertz. We want to convert that to per second because we're working with it. When I ask for a value, it's expressed in hertz. Whenever we work with it, it means per second. Okay, C again is 3 times 10 to the 8th meters per second. And lambda is unknown. So therefore, we have to do a little algebra. If lambda is equal to C over nu, we'll bring lambda up and bring nu down. So lambda is equal to C over nu. Put our values in, 3 times 10 to the 8th meters per second. Divide by 2.944 times 10 to the 14th per second. Our units, seconds cross out, will be in meters. Take your calculator. 3 times 10 to the 8th. 3. And there's a little button here, EXP, or 10 to the x on the calculator. 8th divided by 2.944 times 10. EXP, 10 to the x, 14. And on my calculator, move it to scientific notation, I get 1.019021739 times 10 to the minus 6. But I only have 4 sig figs, so it's 1.019 times 10 to the negative 6 meters. Now, remember, wavelengths expressed in nanometers. We said that 1 meter is 1 times 10 to the 9th nanometers. That way my meters are crossed out. I'll be in nanometers, multiply through. I get 1,019 nanometers. That's my answer. All right, let's try another one. Identify the energy. So this time we're going to go all the way through. That an electron is located if it emits a light emission of a wavelength of 475.5 nanometers. So this is how we find where the electrons are located using mathematical computations. So what values we're going to have? We're going to work with both of them. Nu is equal to C over lambda. What's nu? And E equals H times nu. So therefore, let's start with E. Do I know energy? No. Do I know Planck's constant? Yes, I do. Planck's constant is 6.63 times 10 minus 34th joule seconds. And the frequency, the wavelength, is unknown. Now, can I do a problem if I have 2 unknowns? Well, it's a good thing I have another equation. So I'm going to set that one up. Nu is the unknown. C is 3 times 10 to the 8th meters per second. Remember now, our frequency, our wavelength rather, is 475.5 nanometers. Now, these aren't the same units again. This is nanometers and this is meters. So we're going to have to convert to nanometers. So if we take, we're just going to, like we did before, and take 1 meter on top, 1 times 10 to the 9th nanometers on the bottom, divide it through, get 4.755 times 10 minus 7th meters. All right, so plug those in, and I get 6.309 times 10 to the 14th per second. Now, I'm not going to convert it to hertz because I don't care if what the frequency is. I'm going to use that value. So therefore, E equals H times nu. And H is 6.63 times 10 minus 34 joule seconds. I forgot the line on top. I apologize. And 6.309 times 10 to the 14th per second, the value we just found for frequency. When we do that, my seconds cross out. We get an answer of 4.183 times 10 to the negative 19th joules. And that's my answer. All right, let's do one last problem here before I let you have a crack at it. What is the wavelength? Now, this time we're going to do the same process. We're going to go all the way backwards. We're going to start at energy, and then we're going to find from that the wavelength. Okay, so again, using both equations. If I'm asking for wavelength from energy, I'm using both equations. And I know that E equals 2.9001 times 10 to the 19th joules. I know Planck's constant. I put the line back up there again. That's good. 6.63 times 10 minus 34th. I don't know frequency, so therefore that's my unknown value. I'm going to solve for frequency. So over here, I'm going to move h to the opposite side. So nu is equal to E over h. Take our values and plug them in. 2.9001 times 10 to the 19th joules. Divide by 6.63 times 10 minus 34th joules seconds. My joules will cross out. Take and multiply those through. Now, just so you understand how the calculator works, you don't do times 10 raised to the. Instead, there's a little button either called EE, which I have in my calculator. I also have calculators that have an EXP here on the bottom. That's the button you hit. So all you got to do is put the number in 2.9001 EXP. That gives you exponential, or EE on my calculator, or 10 to the x. That's a third possibility. And negative. If you do times that, it's going to multiply. So don't do that. So just take 2.9001 EE EXP 10 to the x negative 19. Divide by 6.63 EE EXP 10 to the minus 10 to the x minus 34th. And when you do, you're going to get 4.3742 sig figs. I've got 5 here, and this is a constant, so it's infinitely significant. 4.3742 times 10 to the 14th. And again, I don't write it as hertz because I'm not asking for frequency. All right, so we're asking for the wavelength. So I'm going to use the what's new? What's new? Nu is equal to 4.3742 times 10 to the 14th hertz. C is 3 times 10 to the 8th meters per second. And lambda is unknown. Again, so we're going to bring lambda up, bring nu down. So lambda is equal to C over nu. Put our values in, 3 times 10 to the 8th, divide by 4.3742 times 10 to the 14th per second. And I'm going to want to convert to nanometers because wavelengths in nanometers. Meters cross out. I'll be in nanometers. Seconds will cross out here. And we end up with an answer of 685.84 nanometers. All right. So let's try one more problem. This time, pause this. I want to see if you can do this on your own. So we're asking for frequency, and I'm giving you energy. So you're going to have to work it all the way through to you're going to only work it through to find frequency from energy. And there are 2 equations. You have to think about which one you're going to need if you need frequency and you're in joules. Joules energy. All right, so the answer is underneath there. Pause this, work it through. When you're done, start it back up again, and we'll go through and get the answer. Okay, ready? Here we go. So we start with our equation, equals h times nu. Nu is equal to E over h. Plug our values in. 8.115 times 10 to the 19th joules, divide by 6.63 times 10 to the minus 34th joule seconds. My answer is going to be 1.224 because I've got 4 sig figs times 10 to the 15th per second. But again, I don't want per second because I'm asking for frequency. So the answer is going to be 1.224 times 10 to the 15th hertz. Hopefully that wasn't too bad. Take care. God bless. And we'll be practicing 2 days tomorrow.